Hi there. In this section, we're going to look at differentiation formulas, section 2.3. This begins Unit 2, obviously, because you found the video in the playlist for Unit 2. So starting today, this information will be on Exam 2. All right, so let's jump right in. And we're just going to prove a nice formula real fast. Because, as you've probably guessed, we don't want to keep using the definition of the derivative to do work. So what we can do is we can use the definition of a derivative to prove what the derivatives are for a certain class of functions. So for all linear functions, we're just going to prove that the derivative of a linear function, mx plus b, is in fact the slope m. So just thinking about it, this should not be surprising at all. If you have a linear function and you find the slope of the tangent line at a point, well, that's a point on the linear function, so the slope is the slope of the line itself, right? Because the slope doesn't change on a linear function. But we have to prove this, right? We can't just use logic. We have to do proofs. So this is an easy proof, and it's one you might be asked to do on an exam. And then we're going to use part A to prove part B, which is that the derivative of a constant function is always a certain thing. So we'll see that when we get there. So think about it. If a function is constant, think about what its graph looks like, and think about what the slope of that line would be. So let's jump right in. Alrighty. So we're just using the definition, right? So the derivative of f of x, just use the derivative definition. And our function is mx plus b. So we just, wherever you see f of x plus h, you plug m times x plus h. Don't forget the parentheses, you need them. Plus b minus, so we're subtracting f of x. F of x, of course, is mx plus b, all over h. Then we simplify. So just distribute the m's and distribute the negative. Then we're going to cancel. So if you're thinking of, hey, this looks familiar, I've done this before. Exactly, but we don't have to prove this ever again. So once this is a known fact, we never have to prove it again. We can just use it. So everything cancels, right? The mx cancels, you can see, and the b's cancel, right? Mx and b. And so we get mh over h, cancel the h's, and you get m. So nothing surprising here at all. So if this is a test question or something, this is really what I want it to look like. Just show enough steps that that you're convincing me that you know what you're talking about. You don't have to show all of the intermediate algebra steps, and you don't have to write down annotations like now I'm factoring or now I'm distributing. This is fine, just showing the work as long as I can read the work. All right, let's do part B. So we've proven that the derivative of a linear function is just the slope of the line. So that means if we have a constant function, y equals mx plus b, and it's a constant, that means m is 0, right? So f of x equals c for a constant. That's 0x plus c. And because on a linear function, so a constant is linear, you can just read the slope right off of it. That means the slope of the line must be 0. So we just proved a formula. We just proved two formulas. And that's what we do in this section and the next one. We just prove a whole bunch of formulas. And we're going to use those formulas over and over again. So if you guys have those cheat sheets that I recommended you print out, you'll see a whole bunch of formulas on there. There's probably 5 or 6 formulas from this section and probably 6 from the next section. I guarantee they're all on your formula sheet. So that's example 1. Pretty easy stuff. Right? And what I want you to take away from this is that you can write this in words as well, right? The derivative of a constant function is in fact 0. All right, next rule we're going to try to prove. It's called the power rule. So if n is a whole number, then the derivative of x to the n is n x to the n minus 1. So for example, if we take the derivative of x to the 6th, the way you talk about it is you bring the power down on the front, and then you lower the power by 1. So so if you look here and here, you can see it, right? The n comes to the front, and then you lower this by 1. So we're going to prove right now, and this is another proof you have to know, that this works for whole numbers. So before we do the proof, so this is example 2, we're going to prove this formula. So we have to prove this formula before we prove this formula. So look at this formula here. So how do we prove that this is true? So for those of you who aren't accustomed to reading dense mathematical notation, you're going to get a lot of it in this class. So just, anytime you have these iterated powers and the ... it just means continue on. So we have x to the n minus a to the n. Remember, n is a number. So if you had like x squared over a squared, x squared minus a squared over x minus a, you could plug in n equals 2 into this formula and get an answer. So or x cubed minus a cubed. Or x to the 10th minus a to the 10th. You can always divide it by x minus a. And a is a number as well, right? So you could plug numbers in there and verify that it's true. But we're going to prove that it's true. So what does this say? This means you start with x to the n minus 1, then the x power starts to drop, x to the n minus 2, and then eventually this is x to the first, and over here it's x to the 0. And the a power starts to increase as you move to the right. This is a to the 0. Right? A to the 0 is 1, so you just leave it alone. This is a to the first, and the powers keep increasing, a to the n minus 1 and a to the n. So there are n terms, right? And you can count it, right? So remember, we're starting here at a equals 0, or n equals 0 for the a, like it's a to the 0 here. So we're counting all the way from 0 to n minus 1, so there are n terms, right? So now we're going to verify that formula. So you FOIL this expression. So how would you FOIL this? Well, you would take the first term times the first term, the second term times the first term, keep going on down the row, however long you have to go. This is in general. This times this, and then this times this. And then you'd come back and do all of the terms in this again times negative a, and you get this expression. So the expression wouldn't even fit on the slide, it's so big. So it kind of wraps around. And you can see it, right? So x to the n minus 1 times x is x to the n. X to the n minus 1, x to the n minus 2 times a times x is x to the n minus 1 times a. So we have x to the n minus 2 times x, which gives us x to the n minus 1. You just continue on down the line. And so all the terms in this sequence after you FOIL appear here. And it turns out that all the ones in purple cancel because they appear twice, once as a positive term and once as a negative term. Well, when they cancel, you're left with x to the n minus a to the n. Pretty nice. So what that means is that this times this is that. So you can just write it like this, right? So I just set the two things equal to each other. And now I'm going to divide by x minus a on both sides. And then I'm going to cancel the ones on the left side, and you're left with this. And this is what we were trying to prove. This is the formula that we were trying to prove in this example. So what this means is that anytime you see this expression, you can replace it with this expression. And that should look familiar, right? This should look like a derivative, right? Because that's what we're trying to prove, right? Trying to prove the derivative. So now let's prove the power rule for whole numbers, okay? So we're just going to use the original derivative formula with at f prime of a. So this is not the general formula. This is the formula for finding a derivative at a point, as we saw back in section 2.1, where it's the f prime of a. So clearly f of x is x to the n, f of a is a to the n. So this is exactly what we just proved. We just proved that this is this, right? We just proved that on the previous slide. Well, here we can't plug in x equals a because you'd have 0 divided by 0. But after making the substitution, remember, this expression will always factor if you're doing a derivative. So it factors into this, and then you cancel the x minus a's like we did in the proof. And then here we can plug in a for all the x's, right? Because it's a continuous function, right? So we can use substitution. And after you plug in all the a's, it turns out all of these individual terms simplify to a to the n minus 1. So here we took x, replaced it with a. This is a to the n minus 1. Here we have x to the n minus 2 times a. We'll replace this with a. Multiply together is a to the n minus 1. And as you continue across, all these things are a to the n minus 1. Well, there's n terms, so you get n times a to the n minus 1, which is what we're trying to prove. There is an alternative proof in the book if you're interested, but this is the one. This one is much easier algebra, I would think, than the other ones. Actually, both proofs are in the book. But this is the one that you guys should know from my perspective. Okay, so it turns out that the power rule works for any real number. We are not going to be able to prove the power rule until section 6.4. So we're going to prove a different version of this formula in section 2.6, and then we're going to prove the most general version in section 6.4, which is way at the end of the class. It's actually like 2 sections before the end of the class. So even though we can't prove this more general version yet, we're still going to use this rule for the entire course. So just we will prove this formula by the end of the course. Now, we don't prove every formula that we use, but we prove enough that you hopefully believe that we're not just making this stuff up and it's actually rooted in something foundational that you could at some point in the future prove. So there's the formula. So remember that formula. You're going to use it about 600 times this semester. Now, here are more rules. The proofs for these are at the end of the slides. I will go over the proofs. You do have to know these proofs. But in the interest of getting through sort of into more examples, so I'm only going over examples and proofs, basically, in these notes. So in the interest of getting farther along, I'll do these at the end so we can see some examples. So look at these rules real carefully, right? First one, constant multiple rule. So it just means if you have the derivative of a constant times a function, you can factor the constant out. So constants can be freely moved inside or outside of derivatives. That's a really nice feature. The proof will be at the end of the slides. Here's another one, the sum rule. Derivatives can be distributed inside sums. It's pretty nice. And difference rule. The derivative can be distributed inside differences, which is a combination of this and this if c is -1, right? All right, so let's see how to use... Let's see how to use the general version of the power rule, the constant multiple rule, the sum rule, and the difference rule. Let's do an example that uses all of those plus what we did in example 1. So all the rules we've seen so far, including these. And again, you don't have to write these down. You don't even need the PowerPoints. Go get those cheat sheets. All this stuff is on the cheat sheets. All right, so let's do, here's a 3-part example. And we're just going to find the derivative of the functions. So let's start with number 1. Part A here. So f of x equals 2 to the 39th. And so you might be thinking, oh, let's figure out what 2 to the 39th is, right? So you pull out your calculator, right? And you go ahead, try it right now. 2 to the 39th equals, oh my gosh, it's some gigantic number. What happened? Look at that. Well, here's the thing, guys. We don't really care what the number is. The derivative is 0. So think about why the derivative is 0. right? We proved it in example 1, part B. It's a constant. It doesn't matter what the number is. If you're interested in the slope of a horizontal line, it's going to be 0. It doesn't matter how high or low that line is. So that's a very sort of typical calculus question. Problem looks tough, but just think about what it means and you can solve it very quickly. All right, next one. G of x there. So you can see that we have powers, right? So like x to the 51st. We have sums. There's a plus x in there. And we have differences. There's a minus 2x to the 11th and a minus 7. So g prime of x, we just take the derivative. So notice I'm using the operators here. So I'm not sure. So some of you guys have seen calculus before, so you're used to the operators. If this is your first time taking calculus, you've got to get the hang of how to use these operators. There's two main operators that I use over and over again, and I'll introduce them, and then I'll kind of go back and forth between them. Generally speaking, though, most people prefer the ddx, but, it's up to you. We will learn another operator here in a sec. All right, so what do I do? So I want to take the derivative of this whole thing. So am I allowed to just bring this thing in wherever I want? Well, yes, I am. But I'm going to break it down and show you how to use the rules. So the first rule, the sum and difference rules. So I'm distributing the derivative inside all of the pluses and minuses. And generally speaking, you don't have to show all this work, but I could ask you on an exam specifically to break it down using the rules. That's why I'm going over it. I just want you to be aware that the rules exist. Now, you can further distribute inside constants. And that's called the constant multiple rule. Once you've done that, all of your derivatives should be up against powers or linear functions or constant functions, right? So then you use the power rule. So look here. Using the power rule here, so we get this 51 comes to the front, and then you have 51 minus 1, which is 50. It always just goes down by 1. Same thing here, right? We have x to the 11th, so the derivative is just 11x to the 10th. The derivative of x, that's just x to the first, or you can think of it as a linear function with slope 1, so the slope is 1. And this is a constant function, so it's 0. So here we're using the power rule. Here we kind of already proved what to do for linear functions and constants. The main reason I kind of set that aside is it saves us a lot of work. If you recognize a constant function, just write the slope down and you're done, because we proved it earlier. But for these wiggly functions, you really have to show the work. Now you simplify, and you're done. So let me point out something about showing work. Most people, especially if you've seen calculus before, you're ready to go right from this step to this step. And that's fine, okay? I'm not going to make you guys break this stuff all the way down on an exam. I'm going to break it down for the first couple times you see it. You should verify that you know the rules and you know how they work. But on an exam, if you wanted to go straight from this step to this step, that'd be fine. Okay, here's part C. So again, taking the derivative, and this is just a horrible, ugly function. And so you're looking across, and remember, the only rules we have are the power rule, constant multiple rule, sum and difference. And you see something like this. We don't have a 1 over x rule. We don't have a square root of x rule. We definitely don't have a fifth root of x squared in a denominator rule. So what are we to do? First step is always simplify and put everything in a form that you know what to do with it. So if you're doing algebra, radicals are better. If you're solving equations, X's and denominators are better. But when you're doing calculus, we don't really have a rule for these. You have to turn them into their exponent forms so that we can use the power rule. So on the next step, I'm just going to combine sum, difference, and constant multiple just to show you. Again, you are not required to show the work on that, unless you want to. When I was a student, I always did. I got A's. Coincidence? I think not. So look at what happened. The ddx gets pushed all the way in next to x to whatever power, right? So here the ddx gets pushed right here. So it gets factored into the 7. It gets pushed in here, here. It gets pushed inside the negative. Here it gets pushed inside the 8/3. Now we use the power rule, or in the case of this one over here, it's 125 is a constant, right? So its derivative is 0. So let's make sure we understand all these derivatives. Oh, and I meant to mention this in part B. As soon as you take the derivative, notice the ddx goes away. So the ddx as an operator is telling us that we need to find a derivative at some point. As soon as you take the derivative, like as an action, right, then you don't have to write the ddx anymore. In fact, you can't. And then you're left with just an algebraic expression. So the derivative is something that you have to do, but you're allowed to wait to do it until the problem is set up in a way that facilitates easier calculation. It's not possible to just take this derivative just looking at it. Even if you've taken the class before, you really want to put it in a form. At worst, you want to simplify it first. At best, you probably want to implement these new rules just to break everything down and make it real nice. So the ddx went away. So the -5 comes to the front. This power drops by 1. -5 minus 1 is -6. Here, derivative of x to the -1. The -1 comes to the front. The power drops by 1. -1 minus 1 is -2. Here we have x to the 1/2. The 1/2 comes to the front. 1/2 minus 1 is -1/2. And last but not least, x to the -2/5, the -2/5 comes to the front. -2/5 minus 1 is -7/5. So, as long as you're showing work, I don't care how much simplification you do. This is really enough simplification. Just sort of sorting out all the minus signs. You know, like if you have a -0 in there, you can kind of get rid of that. So I'm not asking you to simplify a whole lot. You really just, so if there's like terms, maybe combine those, but you don't have to rewrite everything as radicals and denominators and stuff. You can just leave it in this form. Absolutely fine. So I'll let you guys read that. Here's some more rules. Again, the proofs are at the end of the slides, so I'm going to go over these rules just so you understand it. So this product rule and quotient rule, you're going to use both of these every single day in this class, pretty much. So if you have a product of two functions, the derivative is the first function times the derivative of the second, plus the second function times the derivative of the first. So again, it's easier to memorize these, but if you want to write them down, if you have a little cheat sheet, any of that stuff is fine. Many of you are moving on to Calc 2, and you're absolutely going to use this stuff over and over and over again in Calc 2. And then here's the quotient rule. So if you have the derivative of f of x divided by g of x, it's this very complicated function. Again, I will be proving both of these at the end of the slides. And so it's the g of x, so the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. So it looks funny, but you'll see the proof at the end. It'll make sense. All right, so let's use this product rule and quotient rule. We're going to find the derivatives of these functions. So before I get into the first example, some of you might be looking at these and thinking, well, can't I just distribute this and then just use the power rule? You can. And what about here? Can't I just divide t squared into all these terms and then just use the power rule? You can. But the idea here is that we're still new at this. We don't know how to deal with a lot of complicated functions. So I'm just picking stuff that you could verify on your own using these rules. Okay, so first one up. So I want you to notice here that I'm using this prime notation instead of ddx. Again, I'm going to jump around between both notations in this class. Just get used to seeing both. So here I'm saying the derivative is that entire thing prime. What does that mean? Well, prime just means the same thing as ddx. Okay, they're just two different operators. So here I have a product, so I have to use the product rule, right? It's the first one times the derivative of the second one plus the second one times the derivative of the first one. So notice how I'm rewriting this function using primes. That's the same as the ddx's, okay? The primes remind me that I have yet to do a derivative, right? It's just a little shorthand that says, hey, you haven't done the derivative yet. You're not done with anything yet. Now I'm going to take those derivatives. Notice I did not show the work for the sum rule and constant multiple rule, right? We know that those exist. You are not required to show that work. Just look here and just think to yourself, you know, what's going on with this derivative? Well, this is a linear function, so the slope is just 5. This is just x cubed. What's the derivative of x cubed? Well, bring the power to the front. 3 minus 1 is 2. And same thing here. This is just power rule, right? Bring the 2/3 to the front. 2/3 minus 1 is negative 1/3. So the quicker you can get to not needing to show the sum, difference, and constant multiple rules, the happier you're going to be. So I evaluated the derivatives. Notice the primes are gone, right? So once you've done the derivative, the primes are gone. And you can leave the problem like that, right? This is simplified enough in a lot of ways. You're allowed to keep going. You're allowed to distribute or factor, but I'm really not requiring it unless you have, you know, some really basic things that need to be resolved. I'm totally fine with it staying like this. So it is actually preferred you keep answers in an unsimplified form unless you need to simplify it. So just remember that sometimes you might be tempted to try to do the work in your head and just write down an answer. That does not work on an exam. So you have to show the steps. Even if you can do the work in your head, you have to at least show, if you're using product rule or quotient rule, you have to show those two. You don't have to show sum, difference, constant multiple rule, but you do need to show product rule, quotient rule. And we're going to learn some other rules later. Obviously, it's calculus. There's lots of rules. So just make sure that you're not trying to be in a big hurry, right? You're going to have 3 hours on each exam. So you're going to have plenty of time if you know your stuff. All right, here's the second one. So this, we're using the quotient rule. Notice the prime notation again. So the quotient rule is denominator times the derivative of the numerator. So notice the prime here, minus the numerator. It's got to be in parentheses, times the derivative of the denominator over the denominator squared. So that's your quotient rule. Now I'm going to simplify the denominator and evaluate the derivatives. Right? So 5t squared, bring the 6 up front. So 5 times 6 is 30. Drop the power, 6 minus 1 is 5. Derivative of t squared, bring the 2 up front, 2 minus 1. And then 1 is a constant, so its derivative is 0. Don't even need to write it. And the derivative of t squared over here, of course, is 2t. And I simplified the denominator. And you can leave it like that. There are problems that it might be advantageous to simplify it. So for example, if I said to you, find everywhere that the tangent is horizontal, you really can't solve this expression up here. But if you simplified it, you'd be able to solve this. Right? So that's basically what I'm saying. That that in order to solve sort of like second step, third step, fourth step problems that we're going to see, especially in chapter 3, we're really going to see a lot of that. Just for an exam, I'm totally fine with it being unsimplified. But just to understand that there are some problems later on that you might have to simplify, but you are never required to simplify as soon as you take the derivative, unless, like if there's like a -0 or something, like get rid of that, you know. But other than that, you can leave it basically in a really unsimplified form. Totally fine by me. All right, I'll let you read that. So here's a summary of our formulas that we've learned today. Again, you guys should have a cheat sheet. Everything will be on there. And notice the prime notation is used here on the summary. So the prime notation is really nice. So the first two up there use the ddx. The other ones use the prime. So that's it for the instruction. We're going to finish up this slide with the proofs. So let's go ahead and get right to that, so this video isn't an hour long. All right, here's the proof of the constant multiple rule. So I used it without verifying that it's true, but it should be believable. Well, here's your proof. So we're going to say g of x is c times f of x. So we're just going to plug everything into the definition. Right? So g of h plus x, well, that every time I see, you know, g of h plus x, that's just c times f of h plus x. And then here, minus g of x, so minus c f of x. So look here. This g of x plus h minus g of x, when I replaced it with the f component, there's a c in front of both of them. Well, I can pull that c to the front. Right? Just factor it out, but still inside the limit. Right? The c is still I'm allowed to factor it out because it's multiplied. Why am I allowed to pull that c out front of the limit? Well, limit law 3 allows us to do that. And now this is just the derivative of f of x, which is f prime. So that's an easy proof. Constant multiple. So make sure you understand why these work. Because, again, I could put something like this on a test. All right, sum rule. Here's our proof of the sum rule. Real similar type of thing. We're just going to use big F of x to be f of x plus g of x. So the derivative of big F, right, is this. We just replace everything. So wherever you see big F, so we're just going to take this and plug in x plus h where we see x. This is just that. Oop. Now we distribute the negative and reorganize and group the terms. So we're going to take this negative f of x and bring it over here. Positive g of x plus h, and then this negative is distributed. So that's a minus g of x. So what we've done is just taken both positive terms and both negative terms and rearranged them, turned them into two individual derivatives. Now, I have a sum limit law, so I can distribute this limit, and each of these is just an individual derivative, which is what we were trying to prove. I'm not proving the difference law, but it's exactly the same proof, except this is a minus. Right? If this is a minus, then this becomes a plus, and this becomes a minus, and you get the same thing. So it just changes a sign as you go down. Product rule. So this is a tough proof. Obviously, the one in the notes here is the same one that's in the textbook. because I didn't feel like typing this one separately. So this one, what we have to do is sort of an algebra trick where we add and subtract the same quantity and then group those two quantities and look at what, and then factor and look at what happens. So capital F of x here is f of x times g of x. So f prime of x, just this, capital F prime of x, just this. So we just plug everything in. So here we can't group anything, right? Because we'd have to factor. So what we have to do is sort of like inserting a term that allows us to factor. So what we're going to do, we're going to add and subtract this term here, f of x plus h times g of x in the numerator. So we subtract it here and add it here. And the reason we do that is because it allows us to factor this f of x plus h here out and allows us to factor this g of x out as well. And that's what we get right here. So we have f of x plus h times g of x plus h oh, here it is. Plus g of x. Oh, no, sorry, here it is. Minus g of x. Yeah, here we go. F of x plus h, factored out. Here's the other one. G of x plus h is here. Minus g of x is here. This is just the derivative. When we bring those limits in, we're going to use a limit law and bring those limits in. This is going to become a derivative. Over here, here's a g of x. Here's a g of x factored out. We're left with an f of x plus h minus f of x. Then you use your limit law to distribute the limits inside. So just distribute the limit everywhere you're allowed to. This is just f of x. This is the derivative of g. This is just g of x. And this is f prime of x. So that's a product rule. That's a pretty interesting one. So read it over. Make sure you know what it means. And last one, quotient rule. Very similar to the product rule. So it's the same sort of thing, right? We're using capital F of x here to be f of x over g of x. So when we plug everything in, we have this big stacked fraction. So what we're doing next is getting a common denominator here, right? So the common denominator is g of x plus h times g of x. So we multiply this by g of x plus h top and bottom, multiply this by g of x top and bottom, right? And so that's why you have f of x plus h times g of x minus f of x times g of x plus h. So we got a common denominator, and we just pulled everything together in the denominator. Now here, this is a big ugly mess, and it actually gets worse before it gets better. We add and subtract f of x times g of x here. So here's the subtract, here's the add. And again, it lets us factor. We're going to factor out the g of x here. We're going to factor out the f of x here. And then down here, we're hoping that this h goes away so that we can plug it in. All right. So yeah, that's the same thing on the previous slide. So here's where we factor out the g of x, factor out f of x. So these two things are going to be a derivative, right? So this h in the bottom, we put it back into the individual numerators. Well, the denominators that are in the big numerator. Distribute all the limits, and then plug everything in. This is g of x, derivative of f, f of x, derivative of g, and we plug 0 in here. We get a g of x, and here we get a g of x. You have two of them, so you get a g of x squared. And that's it. So if you guys have any questions, you can post questions on the discussion forum. You can email me, or of course, you can pop in to any of the Q&A sessions that we're going to be having. And that's it for this video, and I'll see you guys in the next video.